the parabolic velocity profile for laminar flow inside a boundary layer. And we also understand that theta, the momentum thickness, the formula for which is integration from 0 to 1 this is the expression for the momentum thickness. So for the laminar case, theta by delta laminar, it would simply be the whole thing where it's going to be 2 eta minus eta square 1 minus 2 eta plus eta square times d eta. So when we do that, and this would be from obviously from 0 to 1. So if you perform the integration, the numerical value of this is simply going to be 2 by 15. So I hope that you do not have any question. I mean, if there are any questions, I'll be glad to answer. But I simply use the parabolic velocity profile, the definition of the momentum thickness, and incorporating this expression for u by u, we would obtain this value. Similarly, for the case of the turbulent profile, where this is corresponding to the turbulent situation, it would simply be again integration from 0 to 1, but for turbulent velocity profile, u by capital U is expressed as the 1/7 power law, eta to the power 1/7. And therefore, this would simply be eta to the power 1 by 7, 1 minus eta to the power 1 by 7 times d eta. If you perform this, this would come to have a numerical value of 7 by 72. Now the momentum thickness theta remains constant, and therefore one would be able to obtain the ratio of delta turbulent by delta laminar. It will be equal to 144 by 105. So this is quite a straightforward problem. Only the definition of the the momentum thickness and the corresponding expression for the velocity profile for turbulent and for laminar is to be used for solving this problem. I move on to the next problem. This I have also explained at in the last class, where I could not write anything. You could see what I write on the screen. Yes, you could see my writing. Just answer yes or no.
Yes, sir.
Okay, thank you. So the problem that we would solve now, in fact, this has been discussed in detail in the last class, that whenever there is a flow through a duct, in this case a rectangular duct, there would be formation of boundary layer over here, and as the boundary layer forms, the amount of mass flow which would pass through from 0 to delta would definitely be less than the amount which would pass through the same region had there been no viscous interaction between the solid and the liquid. So if it's an inviscid fluid, then the velocity would everywhere be the same and equal to the free stream velocity. But since there is going to be viscous interaction, the liquid has a viscosity, so therefore a boundary layer would form and the mass flow rate would be less through 0 to delta here and 0 to delta at the top itself, if this is a rectangular duct. In order to maintain in order to honor the equation of continuity, the amount of mass flow rate through this region, where the thickness of the boundary layer is essentially 0, to this point where we have a finite thickness, therefore the core velocity will definitely have to be more than the 75 or 60 meter per second that we see here. One way to address the problem which has been described in here is to diverge the nozzle slightly in such a way that we would be able to neglect any rise in any change in pressure. So we'll have to have a high for the normal situation, the change in velocity head, core velocity, would be reflected by a change in pressure, and we will solve a problem just after this based on that principle. So the change in velocity would give rise to a change in pressure. One way to address that is to diverge the channel slightly such that we can say with certainty that the pressure gradient is negligible, so that whatever be the core velocity in here would be the same as the core velocity at 1.2 meter as well. So one can write that one can then the problem is why the Bernoulli's equation is applicable to this flow. Obviously, since at the core, at this streamline, it's steady, incompressible flow, and there are no frictions available, no frictions applicable in this case. So the frictional effects are obviously confined in the thin boundary layer. So any streamline outside of the boundary layer for an incompressible steady flow, I should be able to use the Bernoulli's equation. Is that part clear? In the core flow, the Bernoulli's equation is going to be applicable because at the core there is no variation in velocity. All the variation in velocity is confined in the thin region at the bottom and at the top. So outside of that, we would be able to use the Bernoulli's equation. And if I assume that this to be a horizontal one, then the effect of gravity would be negligible. So if I write the Bernoulli's equation between point 1 and point 2, what I have then is P1 by rho plus V1 square by 2. The Z part is not there, plus V2 square by 2. As per the statement of the problem, since the pressure gradient is negligible, I would be able to say that P1 equals P2, which would give rise to V1 is equal to V2. That's the first thing that one should be able to write. There are no questions, I suppose. Okay. The next part of the problem, the next one, I can obviously say that rho 1 V1 A1 should be equal to rho V2 A2 A2 effective. Now this A2 effective is something which we need to know, which you need to evaluate. Now we realize that whenever we are saying that the velocity, whenever we are replacing the velocity at location 2, replacing the velocity at location 2 instead of a varying velocity from 0 to some velocity and a core velocity, I am replacing everything as if the flow is inviscid, replacing it with a constant velocity v2. Now we can do that, and if we recall the definition of the displacement thickness, you replace the situation over here by reducing the area available for flow by an amount which would be equal to the reduction in mass flow rate for reduction in the mass flow rate. So once again, I hope that you remember the definition of displacement thickness, the concept of displacement thickness, the utility of it, and so therefore this A2 effective, if we could write, then the rest would be simple. So what is going to be A2 effective? If we could arrive at an expression for A2 effective, and let's say the depth of the figure, this is B is the depth of the duct. So what is A2 effective? Can anyone tell me what is A2 effective? I am replacing a viscous flow situation by an inviscid flow, and I recall the concept of displacement thickness. The displacement thickness is nothing but when you move the plate up, and in this case down as well, by a certain amount such that the reduction in mass flow rate in this part is equal to the reduction in mass flow rate if we have an inviscid flow case. I just want to get your response since I cannot see you. Are you comfortable with this concept? You do not want me to go through it anymore. I mean, you perfectly understood what I mean by displacement thickness, the significance of displacement thickness. If not, you can always ask me to repeat this. So I assume that you you understand that what is this displacement thickness, and therefore the expression for the area would be whatever be the width minus 2 delta 2 star. This will have to be the this will have to be the multiplied by b. This will have to be the effective area if I use this expression, assuming that it is inviscid flow at location 1 and inviscid flow at location 2 as well. So whatever be the whatever be the situation, that width, and this of course, since v1 equals v2 and it's an incompressible fluid, so what we then have is w2 minus 2 delta 2 star times b would be equals w1 times b, where w1 is the width at location 1, which has been given as 75 millimeters. So the thing that remains right now is what is delta 2 star. Okay, so in order to use delta 2 star that we have to evaluate, first we need to see whether it's a case of turbulent flow or it's a case of laminar flow. For that, you calculate what is Reynolds number, and what you would see that the Reynolds number for this will turn out to be about 4.8 into 10 to the power 6. So definitely this is a case for turbulent flow. The moment it is a case for turbulent flow, then you understand that the relation for turbulent flow is to be used. So use relation for delta in turbulent flow at 1.2 meter. That means wherever we have the second location, from this I should be able to get a numerical value of delta 2 to be this would be 0.02 meters. So with this check with us, then the next thing that remains is the expression for delta star. And the expression for delta star, you know that it's going to be 0 to delta multiplied by 1 minus small u by capital U times dy. And this u by u for turbulent flow, we are going to replace it with 1/7 power law. So this would be equal to eta to the power 1 by 7, where eta obviously is defined as y by delta. So you evaluate this delta star, and this delta star would be equal to about 2.56 millimeter. So therefore the width that we have in here would simply be whatever be the width at the entry. This would be the result for the required width at location 2, such that the change in pressure would be negligible, and the divergence, the required divergence would be provided, that it should be equal to the value, the separation between the two plates should be equal to 80.1 instead of the 75 millimeter, and we could arrive at this with the concept of displacement thickness. So once again, why Bernoulli's equation is applicable that I have explained. This would give rise to V1 equals V2. And if I replace the viscous flow condition in here by an inviscid situation, then V2 is that inviscid velocity which flows through an effective area such that the pressure gradient is negligible. And we could do that once we invoke the definition of delta 2 star. And since we know that the core velocities remain the same, so we would be able to obtain everything in terms of delta 2 star. Check is whether it's laminar or turbulent. If it is turbulent, find out what's the thickness of the boundary layer at this location, and then do the usual steps in order to obtain what is the displacement thickness. And then you know that this is the amount, 2 delta 2 star, both at the top and the bottom, you need to provide in order to obtain the necessary separation between the two plates of the duct for such a situation. Okay.
Sir, when we are subtracting the displacement thickness from W, why are we not subtracting it from B as well?
Oh, okay. That's a very good question. What his question is that if this is a duct, then it has to be what would I say, confined through all sides. Okay, so that means there would be here we have a 75 millimeter gap between the two, but the problem is silent on the depth that we have. Now, this in this situation, to answer your question, though it is not explicitly written in here, we have to assume, you do not have to assume, but in this case it has been assumed that the width B is quite large in comparison to the separation between the two. Now, whenever you talk about such a thin duct, most likely scenario in application would be that it's between two parallel plates. It's as if the flow between two A4 sheets of paper separated by 75 millimeters. So if that's the case, then the width of the duct is large enough to discard, to neglect any growth of boundary layers on the side B as well. And B is not specified in this problem. Had B been specified and it is somewhat close to that 75 millimeter range, then your objection would be 100% acceptable, that we have to have this, whatever I have done over here, it has to be, in this case, it should be B minus 2 delta star as well. But the assumption here is B is quite large compared to W. As B is not specified in the problem, we do not have any other recourse to solve the problem if we do not assume that B is large. Does that answer your question?
Yes, sir.
Okay. But that's a very good point. Normally, for a finite size width, we need to consider development of boundary layer from the side walls as well. I think we have solved one such problem previously when there was a, I think I have it here probably. No, it was in the first part. If you recall that there was a flow through a 305 millimeter square duct. So it's both sides, all sides are 305 millimeter each. So in that case, we have considered growth of boundary layer from all sides. Okay. The
So
next
one more
problem.
question, that
Yes.
when we are considering the delta turbulent at 1.2 meters,
Right.
So usually practically we should be having a laminar flow first, then transition, then turbulent, right?
Absolutely.
So the 1.2 meter, which we're considering from the entry position,
Yes.
should it not be 1.2 minus the distance where turbulent flow begins?
Okay. I will address this problem in the second part of today's class. So what I would say here is that I have used this formula, and this formula assumes that we have turbulent flow from the very beginning. Let me go back to the slide where it says This is the formula that I have used. And I have used that at x equals 0, delta equals 0. That means it's turbulent from the very beginning. I have spent quite some time in the previous classes that why this is going to be an incorrect assumption in some flow situations unless there has been some mechanism by which the flow is made turbulent from the very beginning, or the entire length is small as compared to the total length. So there has to be some sort of a mixed boundary layer assumption, mixed boundary layer approach that is to be taken in order to evaluate what is this delta when we have laminar followed by a turbulent. I did not teach that to you as yet, which is purely based on correlation that I would cover in the second part of today's class. So there you would see that this delta, there would have to be some correction to the delta for cases where there is going to be mixed flow. But you are once again right that I am not very confident about the value of delta 2 star based on this relation since it assumes turbulence from the very beginning. Okay, so satisfied or any other question? But you are absolutely right. It has to be a mix. It probably should be a mixed flow from the beginning. I mean, from the initially, it's going to be laminar, then changing to turbulent. But I would mention it once again is that the growth of the turbulent layer generally is very rapid as compared to the turbulent one. Uh, I will come back to that when I discuss the transition in my second part of the class. Please remind me when I go to that when I show you talk about that part. But right now, yes, I am assuming that it's turbulent from the very beginning, which may not be the case always. Okay. This problem is where we have a flow of air that is it's once again a horizontal duct. We have a well-rounded section. Entrance region, duct height is provided, and it has been mentioned, probably to answer your query, that turbulent boundary layer grows on the duct walls. So in order to do away with any such confusion, it mentions that it's turbulent from the beginning. But the flow is not yet fully developed. So the boundary layer is still growing when I reach the station 2. The 1/7 power law is assumed to be applicable. The inlet flow is uniform with 10 meter per second. At section 2, the boundary layer thickness on each wall of the channel is 100 mm. So that has been provided. Show that for the case for this flow, delta star equals delta by 8. That's the first part of the first part of the problem. We will and then evaluate the static gauge pressure at section 2 and what is the average wall shear stress. And this region, it is still air with a gauge pressure to be equal to 0. That means the pressure outside is atmospheric, and it's still air, so the velocity is 0. So therefore, I have a still air. There is flow through this, and the boundary layer starts to develop. It has been assumed to be turbulent only, and we need to find out what is the pressure at location 2. Is the statement clear to all of you? Do you have any question on the description of the problem? uh, the just quick tell me what is going to, let's say if the pressure over here is P1. If I assume the pressure over here is P1 and over here it is going to be P2, which one is going to be greater? What should be the value of P1, positive or negative? The values of P1 and P2, should they be positive or negative?
Negative.
And you base your statement on which assumption or which consideration?
Bernoulli's.
Bernoulli. So simply it tells you that you have a zero kinetic energy over here. So the kinetic head is 0, and over here you have some kinetic head. So this kinetic head must be supplied by a reduction in something else. And that something else, since it's a horizontal duct, that something else must be a reduction in the pressure head. So P1 is going to be less than P0, and this simply says that in this duct we have a suction that is being operated. So there is a suction pump at this end which pulls the air from the outside, with which was zero velocity, but it imports some velocity over here. So therefore P1 has to be negative. So that's one of the uh, considerations that we need to be clear about when we do solve the problem. So let's first see that we need to prove that delta star is equal to delta by 8. This we have done just done in the previous problem, since delta by 8. Okay, so we know the expression for delta star. So from 0 to delta by 0 to 1, 1 minus small u by capital U times d eta, and we use the 1/7 power law once again. This is becoming a nuisance, but anyway. Uh, so what we have then is delta from 0 to 1, 1 minus eta to the power 1/7 times d eta. And there you would see, after you perform the integration, delta star by delta would simply be equal to 1 by 8. So that's the first part. Now, tell me how you are going to solve the second part of the problem. I need to find out what is P1 or P2. How do I do this? Any idea? In fact, I leave it to I'm letting you do this. Think about it, do it, and tell me what's the answer. But more importantly, not the answer, but how do you do it? First part of the problem is done, that we have already shown delta star equals delta by 8. So what is the gauge pressure at 2?
We can reduce the thickness by delta star and then use the equivalence of mass flow rate, get the velocity, and again apply Bernoulli to get the pressure.
Perfect. Uh, can you say it one step at a time? What are you going to do? Step number 1 and so on.
We have already found delta star, so we can
Right.
calculate the numerical value of it. Then
Yes,
we find out the area at section 2.
correct. The area which corresponds to delta star, that means the area when I incorporate the boundary, the displacement thickness into my consideration. Therefore, the entire flow situation at 2 is replaced now with the new area that you have just described. Right? That's what you are saying.
Yes.
Okay, so that once I have this delta star, and once again I would assume that the width of the duct is too large, so any growth of boundary layer on the side walls will probably not affect my final results. So therefore I neglect that part, and therefore my new area available for flow at location 2 would simply be equal to H minus 2 delta 2 star. Anyone having any question, any problem, please let me know. So that's what you have said. So what did you do after this exercise? What did you get?
So the mass flow rate at section 1 and section 2 should be same.
Right. So
So we can find
essentially,
out velocity at
let
section
me let
2.
me write what you are saying. You are saying that mass flow rate at location 1, and I mean all the locations are going to be same. So your V1 A1, whatever that velocity is, so simply this is going to be V1 times W, where W is the width, which is large compared to H, and this should be equal to V2, A2, and this is the mass. This is the continuity equation which you have, which you are saying, and then what you are saying is that V1 A1 should be equal to V2, and instead of A2 it should be W, where W will cancel from both sides, but this length is going to be 2 delta 2 star. This is what you are saying. So essentially, what you have said is that from this relation, since V1, A1, everything is known explicitly, the numerical value is known to us. So V2 should be, we should be able to calculate V2, and this value of this V2 you would find after you plug in the numbers should be 10.9 meter per second. Compare that with what we had in here when it just enters the duct. The velocity was 10 meters per second, but over here at the core, when I replace the flow situation to make it inviscid, I reduce the flow area. So when I reduce the flow area, obviously the velocity has to increase, and this is the increased velocity if I assume inviscid flow throughout by incorporating the delta star concept. Okay, what's next then? What did you say?
We can apply Bernoulli again.
Bernoulli's equation. So I would use the Bernoulli's equation over here, plus V0 square by 2. That's the location outside of the duct. So this should be equal to P by rho plus V square by 2. And this P could be P1 or P2. We realize that this is still air. So V naught is simply going to be equal to 0. And if I try to find out what is the pressure at location 1, and I emphasize that this is the gauge pressure, so this would be P1 minus P naught, and it would simply be equals minus half rho V1 square. So if you put the values in there, this would be minus 61.5 pascals. And similarly, you should be able to write what is P2G, the gauge pressure at 2, which would be equal to minus 73 Pascal. So these are the two pressures that you would obtain simply by invoking Bernoulli's Bernoulli's equation and the concept of displacement thickness. What is left is the third part. The critical part is what is the average, and I think the key word in here is average wall shear stress between the entrance and section 2 at L equals 5. So L, the length in this case is 5 meters. And we need to find what is the average wall shear stress. The way to do that is to make a balance. So I am going to make a momentum balance using a control volume which is half the height of this. Okay, the other half would simply be identical. So we will take half the height and find out what is the momentum, convective momentum that comes in, the convective momentum that goes out, and since this the height over here 150 millimeter, that is way above this, so I should be able to I should be able to neglect whatever these are the two inflow and outflow in these two cases. There is also going to be a pressure which is acting over here and some pressure which is acting over here. So there is going to be a pressure force acting on the control volume as well. The third one is there is also going to be a shear which is acting on the control volume. Can you tell me the plane on which this shear is acting? Is it the top plane, the bottom plane, the side one, the side at 2, or the side at 1? Where do you think the shear is acting?
Bottom.
Okay, so what I have done essentially is I have taken half. This is my control volume, which is right at the half. So P1 is acting on this area, P2 is acting on this area, there is no shear at the top, since the velocity there is constant, there is no velocity gradient. Since there is no velocity gradient, there cannot be any shear. Over here, I have a tau w. If I express the wall shear stress to be tau w, that is essentially the shear stress or force, the shear stress felt by the plate. So the stress felt so the stress felt by the fluid would be minus tau w. That's all we need to evaluate. And I need to find out what is the momentum that is coming through this face at 1, and what is the momentum that goes out through this face at location 2. So let me now then draw it clearly and try to see it's meant by what I mean by this. So this is my location 2, location 1. This is 5 meters. I know what is P1 over here, what is P2 over here, and there is uniform flow in this case. And up to this point, there is going to be a flow which is this is the boundary layer thickness. So over here, the mass flow rate is going to be different as compared to equivalent thickness at this point. So I need to find out what is the momentum flow out and what is the momentum flow out over here. The velocity at one over here is going to be equal to v1, and the velocity in this part is going to be equal to v2. But what is the velocity over here, that I am unsure of. So if I apply momentum equation in this case, then there is no body force acting on it. It's a horizontal duct, and it's a steady state situation. So the first term on the right hand side of the momentum equation, del t part, would be equal to 0. So what you have then for the momentum equation, and I am writing the x component of it, Fsx would be whatever be the convective flow of momentum. This is u rho v dot dA. This is what it is. That's going to be my governing equation. Now this Fsx will have two parts. One part is going to be P1 minus P2 W times h by 2, where h is the height of the duct, or the separation between the two plates of the duct, and this is the pressure force, minus tau average, which is essentially tau w times L. So this is going to be the shear stress acting on the element of the control volume that I have drawn over here, and the bar simply denotes that it's an average value. Whenever we use integral equations, we always refer to average values and not absolute values, not point values. So tau bar is whatever be the shear that we have, average of that between location 1 and location 2. Then I come to the right. If any question up to this point? Okay. Then I come to the right hand side. The right hand side, the velocity is v1, and the mass flow rate in this case is simply going to be rho v1 times h by 2 into w. That's the area. So rho v1 a1, and multiply it with v1, which is the constant non-zero velocity at location 1, which is v1. Any change that you suggest to whatever I have written? Anything that I need to incorporate in here to make it correct? do you think that the right hand side, the way I have written is correct? There is obviously going to be a momentum flow out through 2, which I am yet to write, but the expression that I have written for momentum in through the surface at 1, is that correct, or do you like to modify it? Anything that is unconventional, which I have written on the right hand side. Unconventional means something that we have decided at the very beginning itself that I am not following over here. See, this answer should come from you.
V1 is not constant throughout the section.
Now V1 is constant throughout the section, so we go back to this. This is V1. At the entry point of the duct, V1, I mean the velocity at 1 is constant. So V1 is 10 meter per second everywhere. At location 2, obviously it is not going to be constant. Up to a certain point, there is going to be the presence of the boundary layer, and beyond that point, we do have mm, a constant velocity. So I go back to this. What I have not included in finding out the momentum through location 1. Is it momentum in or momentum out? Momentum into the
In.
control volume? In. So if it is momentum in, then what did I miss?
Negative sign.
Yes, that's what I have missed in here. There has to be a negative sign in this case. Okay, so do not forget that our convention must be adhered to, that anything in is to be treated as negative, anything out is going to be positive. Now let's concentrate on location 2. If this is my location 2, then the velocity profile would probably look like this. Up to certain point, the velocity will vary, and beyond that point, the velocity will not change. So this thickness of this is obviously going to be 0 to delta 2. So and it is momentum going out of 2. Momentum, if it goes out of 2, it's going to be positive. It's going to be positive. So what we have then is but I have also need to include the momentum which goes out through flow through the boundary layer, which is u rho u w dy. Did you see what I have done? I have simply divided the flow into 2 parts. This is part 1, which is this term, and part 2 is this term. So because of the constancy of velocity at location 1, I only used V1. Because of the varying nature of velocity between 0 to delta 2, I have added this term, and beyond which the velocity is constant, so I have used this term. And in all cases, since the momentum is going out of the system, so therefore it will be treated as positive. So that's all that we have in this problem. Okay. There's one more. So what I should do next is then simply I need to evaluate what is. Let's say I'm evaluating the last term over here. If I call this as A, So I'm evaluating the only thing that I would like to show you the evaluation of the last term. It would simply equal to rho v2 square delta 2 nw 0 to 1 eta to the power 2 by 7 since I have the velocity square times d eta. So I have used the 1/7 power law since it has been mentioned that this is turbulent, and therefore I use the eta to the power 1/7. So this A, the term A, would simply be equals to rho v2 square 7 by 9 delta 2 W. You could substitute everything because all terms in here are known. You have evaluated what is P1, P2, W, H, etc. known to you. V1 is known to you. V2 you have calculated. The integral you have calculated as well. And therefore, you would see after you plug in the numbers, this would be equal to 0.3 Newton per meter square. So that's the average wall shear stress which you would have in this case. So another use of momentum integral equation which tells us that what's going to be uh, how to solve this kind of a problem. So I have solved a number of problems to clarify the concept of the laminar to boundary layer transition, how to handle turbulent boundary layers, what is the universal velocity profile, what are the other velocity profiles uh, that we may have, which is called universal velocity profile. But if you look at it carefully, it's not universal at all. And if you strictly like to confine yourself to analytical approaches, then substituting the time fluctuating component in Navier-Stokes equation, which would give rise to three additional terms for the x component itself, which are collectively called as Reynolds stresses. So that's what I have covered in this part. So turbulent flow, time fluctuation, Reynolds stress, Prandtl, using Prandtl's approach, something called universal velocity profile, something completely empirical, which is the 1/7 power law, which fits the data well for the velocity, but it fails near the wall. So we need, and the near the wall, it is not only the tau w not only involves velocity, it involves the velocity gradient, which would make it even more difficult to use. So I could use the 1/7 power law inside the integral sign, but not over here. So for this, I use the Blasius correlation, where we know that this is the H in terms of F. F is for a smooth pipe is this. So I have an expression for tau W, which I plug in to the momentum integral equation, use the somewhat unrealistic in some cases condition that it's turbulent from the very beginning. I obtain an expression for delta. I obtain an expression for the friction coefficient, and then I have solved these problems to uh, establish what it is in such a case. Any question? Okay, so what I would do is I will take a 5 minutes break, then I come back and finish this boundary layer chapter, where we are going to concentrate on the drag coefficient, and we have one or two interesting problems to solve before I close this part. So break for a few minutes now. Okay, so let's start once again. Uh, this should be the last lecture on hydrodynamic boundary layers. So we'll discuss about thermal and concentration boundary layers later on. So this is the starting slide, which you are already aware of. But what we are going to do in this this part of the class is very quickly go through. Uh, okay, first of all, can you see the slides? Can you hear me and can you see the slides?
Yes, sir.
Okay, all right. I hope this class will be more interesting because I'm going to show you something. Uh, uh, we'll see. So when we talk about fluid flow through immersed bodies, there are obviously some shear forces which are going to act. The immersed body is going to experience some force due to shear and some force due to pressure. Both are essentially forces which are acting on the body surface, even though the surfaces in those two cases would be different. This should be the frontal surface, or in many cases for irregular objects, this is going to be the projection of the whole thing into a plane which is perpendicular to the direction of flow. Whereas the body surface that I talk about here is the surface which is parallel and in contact with the fluid, and that's what we mean by shear forces. That's where the shear forces act. And in this part of the course, we are going to consider only the first one, where the shear one. And the shear force is, in most of the cases, is commonly called as the drag force. And this is the definition of the drag coefficient. So the drag coefficient is the force of drag, force due to shear, divided by half rho v square A. If you compare this with the definition of the friction coefficient that we have introduced, there this Fd is to be replaced by tau w and by the dynamic pressure, so it would be only half rho v square. So tau w by half rho v, or tau by half rho v square, that's the drag coefficient, whereas the Cd is essentially the total force due to drag divided by half rho v square. And this CD, this you know from various forums you have come across this, that CD is going to be a function of Reynolds number. If the Reynolds number is very small, and I mean in the range of 1 and around 1, and then let's say if a sphere is falling in a stagnant fluid, a stagnant liquid in most of the cases, stagnant liquid, then what we get is the Stokes law, which would be valid only for low values of Reynolds number. So when I need to calculate the flow force, entire force over a flat plate parallel to the flow, because that's the first thing that one would try to obtain, because that's a very standard situation that would give rise to some equation, some relations upon which we can build for more complicated cases. So the friction drag, like many, would be first evaluated for a flat plate parallel to the flow. And this Fd, by definition, is whatever be the local force, which is tau w times dA. We understand that this tau w is a function of x, as I have mentioned. So since we are integrating it over the plate surface, so therefore this Fd will cease to be a function of x, and that's the beauty of CD, where it's location independent, but it will depend on Reynolds number. So this is the definition, and for laminar flow, we know what's the expression for CF, so we would be able to obtain what is the expression for CD in this case, and therefore you would find after you perform the integration, what you would find is CD to be equal to 1.328 by RE, and I have circled L, the subscript L, in order to show that this CD is based on the total length of the plate, and therefore it is not a function of axial location on the plate. The difference, the fundamental critical difference between CF and CD. So we have an expression for CD in laminar flow. In a similar fashion, one would be able to obtain what is going to be the CF for the case of turbulent flow. And we also realize the relation that we have for turbulent flow. When you substitute that for exactly the same way as before, I am not going through all these steps. What you would get is CD to be equals 0.072 by RE. Once again, L is circled to show the independence of the independency of the actual location, and this is valid roughly for Reynolds number less than 10 to the power 7. If the Reynolds number is greater than 10 to the power 7, then a purely empirical formula for purely empirical relation for CD is commonly used for engineering calculations, which is this. Okay. Do you have any question on the fundamental concept of CD? How does it differ from CF? How to evaluate CD for the case of laminar flow and for the case of turbulent flow? Any questions that you may have? All right, so we realize that these are the three relations that one need to use in order to obtain the CD and therefore the total drag force acting on a surface. Coming back to the one which we were discussing so far but did not address, and also in the last class there's a problem where I said that the flow may not be turbulent from the very beginning. But I would like to point out here is that in engineering calculations, we are mostly interested in what is the drag force, not what is the thickness of the boundary layer. Okay. So in order to calculate the drag force, whatever you get, assuming turbulent flow from the very beginning, a proportional amount is to be subtracted in order to account for the presence of a laminar region at the beginning of the flow. So this is the relation for the turbulent flow when the Reynolds number lies between the range of 10 to the power 7 to 10 to the power 5 to 10 to the power 7. You could derive that by using a proportionality law, a proportionality rule, that how much is to be deducted from the value of CD based on purely turbulent flow from the very beginning. And the only information that you would require in order to obtain this number 1740 is that the laminar to transition is going to take place at a Reynolds number of 5 into 10 to the power 5. So if you construct a triangle, use the principles of proportionality, then you would be able to arrive at this solution, which I am not doing, which I am not performing over here. So this is the relation that one would obtain. And if the Reynolds number is greater than 10 to the power 7, then we have to go back to this empirical formula. And in a similar fashion, some amount is to be subtracted, where once again you would be able to evaluate that the amount to be subtracted is this. So my point here is that when it is turbulent, we are not too much bothered about what is going to be the thickness of the boundary layer if we assume laminar flow or if we assume turbulent flow. But it is going to make a substantial difference when we try to find out what is the value for the CD. Now, in many situations where you are calculating the drag force on moving objects, and the common moving objects that you would see are, let's say, the length of a car, the length of a tanker, a super tanker, if you are talking about transporting a crude oil from one continent to the other. In most of these cases, the super tanker is a huge length. It's almost like half a kilometer or so. If that's the case, then the region in which the flow will remain laminar is extremely small compared to the total length. So it's a customary to take the flow to be turbulent from the very beginning of the tanker itself. For the case of a car, the length may not be, obviously will not be as large, but the velocity is going to be substantially more. So you would reach this turbulent flow condition that 5 into 10 to the power 5 within a very small, very short car length, indeed, compared to the overall length of the car. And therefore, the expression for CD can be used in the turbulent flow expressions. But my point would be, since we have some correlation for the case of mixed flow, so it's better to use this relation, and we would see that the effect of this is going to be negligible because of the Reynolds number 1. The Reynolds number is going to be too large as compared, and even now itself you could see that it is 10 to the power 3, and over here it's 10 to the power 5. And if you go to higher values of Reynolds number, which would take place if you have a large length, or a high velocity, then this Reynolds number, the REL, is going to be so large that the contribution of these terms will be rather small, will be almost negligible, insignificant on the overall value of CD that you would obtain by assuming turbulent flow from the very beginning. So is this part now clear to you that the occurrence of mixed flow and the so-called insignificant nature of mixed flow in terms of affecting the value of CD? That's what I wanted to convey through all these relations. Okay. Any questions so far? All right, but once again, I note that this CD is not a function of X. The CF, the expression for CF that you have, you look that this is as a function of, this is REX. You look at CD, this is REL. So that's the difference, one of the major difference between CD and CF. And this figure you have seen before, somewhere in your physics book maybe. It's a figure of a drag coefficient as a function of Reynolds number. And what you see is that initially it's going to fall slowly, and the linear nature, this linear part is the Stokes region, and thereafter when it hits the turbulent flow, then the CD decreases suddenly. So this sudden decrease of CD at the onset of turbulence will have some very interesting implications in a practical in a situation that I would clarify more, that I will describe in more through a problem. But what we see here is that the experimental value of CD for a sphere as a function of Reynolds number shows a sharp fall in its value as we move from laminar to turbulent, but then it starts to increase. Okay, and in turbulent flow, let's say if we are talking about a ball, then when it becomes turbulent, then it starts to separate from the moving ball itself, or moving object itself, moving sphere, and a wake is formed at the back. The wakes are low pressure region, whereas at the front that's going to be stagnation pressure. So this is a high pressure. This is going to be a high pressure region. The presence of these wakes impart instability, and therefore there are attempts to break these wakes into smaller ones by incorporating structures on moving objects like the fins, like the tail. At the tail end of a moving car, you'd have the spoiler, which essentially breaks the wakes to give more stability to the car. And I think I have discussed this with you before. Now, not only you have wakes formed when an object moves, when a spherical object moves in still air. When any object moves in air, for example, there would be the formation of a wake. So this is the low pressure region. So if this is a sports car and a wake, that means the low pressure region has been formed just at the wake of it, then another car, the car following the lead car, would like to be its nose in the wake created by the front car. So that the pressure drag felt by this car would be less, since it is experiencing a pressure which is less than the pressure it would have experienced had it been moving at a point far from it, or at a point far back of it. So that's why you see the specific pattern of cars following each other in a very tight, compact form, where the lead car may not win the race, because the other cars, the smarter cars, would like to be at the wake created by the lead car and overtake it only at the last lap to gain, to reduce the number of pit stops and to reduce the wear and tear on the tire of the car. So these are some of the very interesting applications of the formation of wakes the breaking of the wakes and following each other in competitions, be it motorcycling or be it in a car race. Uh, I have two problems. The first problem is straightforward, and the second problem is I would like to spend some time on the second problem. The first one is any questions so far? Okay, so a particle of 1 millimeter diameter and some density is falling freely from rest in an oil whose density and viscosity are provided, and we will assume that the Stokes law is applicable. How long the particle will take to reach 99% of its terminal velocity? So we all know that any such particle will reach some sort of a terminal velocity, but we would like to find out like what is the time it would take to reach 99% of the free stream velocity. So the of course the governing equation would simply be m dv dt, that is mass times acceleration, would be the forces acting on it, and the forces acting on it are the due to gravity, due to buoyancy, and of course there is going to be a drag force which is acting on it. So this is the same principle. You have seen the application of this in the case of rotameter in fluid mechanics, where the three and the rotameter, when the rotameter looks something like this. There is a tapered tube and a float. The flow is from here. The rotameter, the float has higher density than that of the liquid. So in absence of any flow, the float would come and settle at the bottom. But since there is flow, it's going to move up because of the combined action, of drag, and there is a buoyancy force, and it would come to a new steady location, since as it moves up, the area available is becoming more, the velocity therefore will decrease, and as the velocity decreases, the drag force is going to be less. So at equilibrium, when it reaches a new equilibrium, the algebraic sum of these three would be equal to 0. That's the working principle of a rotameter. But here we are working on here we are solving a different one, in which case the ball is falling, which obviously with some acceleration, it is reaching a velocity. It will reach the terminal velocity after some time, and we need to evaluate this time. So this is the governing equation. Now, therefore, this dv dt would simply be this would be the expression, and we know what is this is the drag force. I would rather write drag over here, and the expression for drag force is known to us. D is the diameter, V is the velocity. We know what is the mass of the particle as well. And we also know what is m naught in this case. So after you substitute everything, the expression for the final one rho naught is that of the fluid. This would be your expression, and then you should do the solution of this equation, which I will not do, and then you should be able to obtain, when the velocity reaches 99% of the settling velocity, you should be able to figure out what is the settling velocity. So find out what is V settling from the above equation by setting dv dt to be equal to 0. Your final result would be 0.00. This would be the final one, and you could the terminal velocity would be 3.6 into 10 to the power minus 3 meter per second. And since you are using Stokes law, you should always check what is the value of the Reynolds number, and when you do that, it will have a value equal to 0.11, so quite less as compared to 1. So therefore, the applicability of Stokes' law is verified. Okay, so that's a straightforward problem which one can devise around this. Now comes an interesting part of the some other interesting problem. Um, I think most of you are well aware of. I mean, you like or you have seen cricket, and you have seen the action of the first bowler, where the bowler use depends or relies on space to beat the batsman. But there are a certain class of bowlers who do not bowl as fast as a fast bowler, but they judiciously use swing with medium pace and to beat the batsman, because how the ball approaches the batsman in an unpredictable way, at least to the batsman. And they do rely on the movement of the ball in air, not off the seam. That means not off the pitch, but while it comes towards the batsman, it will change its direction while it is in air. Now, I think all of you have seen a cricket ball. A cricket ball is characterized by the presence of a seam. I mean, you have seen, all of you have seen a cricket ball, right? How many of you uh, mm, have taken a ball at hand to see what it is? Let's see how many of you are here. Maybe about 20. Is there anyone who has who plays cricket? Who has thrown a cricket ball ever in their life? Anyone? No one has seen or touched or held a cricket ball. This is
Yes.
you have done. Can you
Yes,
describe
sir.
what is unique about the about a cricket ball? From a tennis ball, a cricket ball, how does it differ?
There
Let
is
me,
like one line of protrusions, like the stitches.
what is that called? Yes. Can you see this? Can you see the images of cricket ball that I have?
Yes, sir.
Okay. So the line, the protrusion that you are talking about is this one. So this is called the seam, where these two sides are stitched together at this end. So this is the seam, and the medium pace bowlers use this seam to make the ball move while it is in the air and coming to the batsman. That's called a swing ball, and it could be an outswing where while coming towards you, it will move away from you. So if you are committed to play the ball in a specific way, it will most likely take the outside edge of your bat and will result in a catch to the wicketkeeper or to one of the slips. There are other if the seam is directed towards your leg or towards the leg slip, then from outside the off stump, the ball will come towards you. And once again, you are going to be completely beaten unless you can read the hand movement of or the seam position of the ball while it is being released from the hand of the bowler. So that's why you have the screen at the back where you can clearly see the red ball and more importantly the location of the seam the moment it is released from the hand. So it is either inward or outward, and depending on that you are going to have the you are going to have this inswing or the outswing. Now I'm going to show you two video, and there is a third class of ball where the ball is going to come straight towards you. But while it has crossed mid pitch, somewhere around the middle of the distance between you and the bowler, then it starts to move in one of these directions, in or out. If that happens, it is called a let swing, and let swings are impossible to play because your body, mind, or the coordination, body and mind coordination is such that the moment the ball starts coming towards you, in that fraction of a second, your foot and your bat will have to be in the right position to arrest to hit the ball, to block the ball, to arrest or to act in a direct to act to counter the in swing or the outswing. But if you see, if your eyes see that it's coming straight towards you, and you commit to play in that position, and then at the last moment you see that the ball is going away from you, you won't be able to take your bat out of the line of the ball. Or if it suddenly starts coming towards you, you are tempted to let it go, but then suddenly at the last moment it starts coming towards the stamp. So that's what a let swing is. And everything depends on turbulent flow and laminar flow. In fact, the boundary layer. So bowlers probably unknowingly use the concept of boundary layers while bowling swings, outswings, in swings, and more importantly, let swings. And you have also seen that there is what the bowlers and the fielders do is they always polish one side of the ball without touching the other side of the ball. Okay, so when they polish this side, they make this surface smooth, but will keep this surface rough. So all of them decide that this is the side, this is the side that I am going to polish. This is the side we will leave as it is. So you're going to have a smooth surface on one side, and you are going to have a rough surface on the other side. Based on this discussion, why can you tell me why would the ball swing? I have given you enough indication to arrive at some sort of an answer.
Different forces on the different sides of the wall.
Is it different forces? Obviously, it has to be a different force. There's going to be some force on one side, some other force on the other side. But what causes this difference?
One side might be laminar, the other side
One
turbulence.
side might be laminar, the other side might be turbulent. And this can be further influenced, further enhanced if you hold the ball like this. So when the flow of air comes in, while it goes through this side and while it goes through this side, in one path, it encounters the seam. In the other path, it does not encounter the seam. So if it does not encounter the seam, the flow is probably going to remain laminar. But if it encounters the seam, then it is going to be turbulent from the very beginning. So in other ways, this seam can act as a turbulence promoter, creating turbulent flow all everywhere on this side and keeping the flow laminar on this side. So if you have laminar and turbulent on different sides, then the forces acting on them are going to be different, which would cause the ball to move in air in a way which would be completely unknown to the batsman when he or she faces this kind of a ball. So with this background, with this background, I'm going to show you two such balls. There can be many examples, but these are the two examples which I'm. Can you see this video?
Yes,
I
sir.
just played it for 1 second. Could you see it?
Yes, sir.
Okay, so let's see what happens to the bowler when he bowls and what kind of trajectory it takes. Look at the projection. So you could see that how it changes its direction. But the best example of lead swing is, I mean, you have definitely heard about him. Is one of the greatest of all, the Pakistani bowler Wasim Akram. So if you see his ball, this is one of the best example of lead swing that you would ever see. Yes. Look at this one. So you could see how the last in the last clip, the ball has moved in the air, and after crossing some distance, then sharply it turned inwards towards the stump, and the batsman was right in front of it when that happened. So that's a perfect example of a leg swing. So our next and the last problem on boundary layer is based on that. Uh, The laminar to, let's look at this one. The laminar to turbulent transition on a new cricket ball, the diameter is specified, occurs at a Reynolds number of about 1.4 into 10 to the power 5 if the flow does not encounter the seam. But it can be triggered by the seam at a Reynolds number as low as 9.5 into 10 to the power 4. So from 1.4 into 10 to the power 5, the transition, the turbulence can take place when the Reynolds number is 9.5 into 10 to the power 4. Use this above information to advise a seam bowler about the speed at which he has to bowl to achieve swing of the ball. The kinematic viscosity of air is provided. You tell me what would be the solution. Think and then answer. Mechanically, if you look at the problem mechanically, there are two Reynolds number given and the kinematic viscosity is known. So you should be able to, it's easy to get there are two velocities. So let's say there is one velocity. So it's essentially Reynolds number times nu divided by d, where d is the diameter. So in one case, you're going to put 1.4 into 10 to the power 5 into whatever the value of nu that is provided, whatever the value of the diameter that is provided, meter per second. So you get 1v to be, if you convert it to kilometer per hour, one is going to be 105 kilometer per hour. If you use the Reynolds number RED to be 9.5 into 10 to the power whatever 10 to the power 4, you get this V to be equal to 71.25 kilometer per hour. So if you just use the value of the Reynolds number that has been provided, you will come up with these two velocities. But you have to give a logic now. What is going to be the speed at which the bowler has to bowl?
So speed should be it in between of this.
Can you explain what happens if the velocity is more than 105?
So the force will become turbulent if
Can you say it once again? I didn't catch all of it. If it is more than 105, let's say it's 110 kilometer per hour. What happens then? You are absolutely right. Just say it with confidence.
say it may be that there is no seam or the flow will become completely turbulent.
On both sides.
Yes, sir.
That's
So
the
the
that's the part
seam,
you
the
are
swing
testing.
will not be happen.
Exactly. So let me rephrase. There is some problem with your connection. I understood what you have to say, and you are absolutely right. If the velocity is more than 105 kilometer per hour, then irrespective of whether you encountered the seam or not, the flow is going to be turbulent on both sides. And if it is turbulent on both sides, it's not going to move while traveling in air. And what is the what can you say about this 71 kilometer per hour?
So for 71, it may be the laminar both sides. Then
Exactly.
also the swing will not happen.
Exactly. So if the velocity is less than 71 kilometer per hour, then whether you encounter the seam or not, it's going to be laminar all the time. So if it is laminar on both sides, so if it is laminar on both sides, it doesn't move. You need to create a condition in which it is going to be turbulent on one side and laminar on the other side. That will only happen when the velocity is within this range, which would be laminar on one side and turbulent on the other side. So that's why in order to have swing, your velocity will have to be in between this range. I would call it as V upper. So let's call it as the upper limit of V, and this is the lower limit of V. Is it clear? Anyone having any question? So that's one of the reasons why the fast bowlers do not get any swing, because their speed is more than 105 kilometers per hour, roughly in that range. And that's why the spin bowlers or the slow bowlers do not get a swing. They rely more on off the pitch movement rather than in air movement. But a swing bowler depends on in air movement and by creating laminar flow at one end, at one side, and turbulent flow on the other side. Okay, any question? This next part is we have to, as I mentioned about the leg swing. Leg swings are referring to ball that swings unpredictably late in flight. Uh, and you have been given certain numbers. A cricket ball whose mass is provided, the diameter is same as before, being bowled at a speed V naught greater than the critical speed of the previous problem. And by greater than the upper critical speed, so greater than 105 kilometer per hour. So he has the bowler has bowled at 108 kilometer per hour, let's say. So if it is more than 108 kilometer per hour, then of course it's going to be turbulent on both sides and it will come straight towards you, right? Because it is turbulent on both sides. Your velocity is more than 105, so it will have turbulence on both sides. The drag coefficient in this situation, as the ball moves in air, is about 0.15. Estimate the velocity at which the ball must be bowled so that it starts to let swing at a distance of 15 meters from the bowling end. So almost half the pitch has been covered, and then it starts to move in a specific direction. Okay, so let's concentrate on this part first. Estimate the velocity. This part, the velocity at which it must be bowled so that it is going to uh, it starts to let swing. Can you tell me first, describe the physics to me, and then you can express it mathematically. What is the physics?
The drag coefficient or the drag force will slow the ball down, and when the ball reaches 105 km per hour, then the swing will start.
Perfect. So I start with some unknown velocity, whatever, 110 or 115 or whatever it is. And then because of drag coefficient, the ball will start to slow down in air while it is coming towards the batsman. And then when it reaches 15 meters, is that 15? When it reaches 15 meters, its velocity must be equal to 105 or whatever velocity that we have calculated from the previous one. And since it's 105 and falling once again, so therefore it's going to have laminar and turbulent flow. I mean, one side laminar, one side turbulent. So whatever you have written, if you want to express it mathematically, what would that be? The mass of the cricket ball is known, and of course it's going to have a deceleration because of the presence of the force. And the opposing force in this case would simply be the drag force. So one should be able to write that whatever be the drag force, this should be equal to minus m dv dt. That's the governing equation. Any question? And the drag force by the definition of CD would simply half rho v square pi d square by 4. Note that this is always the frontal area. Okay, this would be equal to minus m dv dt, minus m dv dt. And we know that this CD, the value of CD is provided as 0.15, which is a constant. And everything else on the left-hand side is known. So you have a complete expression for dv dt. And you can integrate this equation to obtain what is the time. And what would be the limits of this integration? One is obviously from 0 to t, and for the case of v, it should be what would be the limits on v?
V naught to 105.
V naught to 105, where v naught is the velocity with which you are going to ball it. So it's at 0, it's going to be some value of v naught. To t, it's going to be v, whatever one that we have, v upper. So and that would give you what is the x, sorry, and the x is provided, the distance is provided as 15 meters. So this being the unknown, you should be able to evaluate what this V naught is. And we know this V, whatever V naught, or this you would see the result of this is 1.03 V upper. This is the expression. Is there any question on this part? It's a very simple problem, but it is so interesting to look at when you solve when you express the concept in terms of a problem that is very interesting and relevant and contemporary to look at, you feel better, you understand more. That's what I feel. So I have chosen this specific problem to reiterate the concept of CD, the effect of drag, how it slows down or speeds up, and also the transition between laminar to turbulent in the form of something with which you can relate to. So the last part is from your calculations, do you feel that a swing bowler can plan his delivery for a late swing, or whether this delivery is just a matter of chance? What is your impression based on the final result? What if the velocity is 1.05 times v upper? What would happen?
It will swing even later than 15 minutes.
Or it will probably reach the batsman before it starts to swing. So the batsman will have batsman will have no role to, I mean, no problem to play it in a specific way, considering it is a fast ball which is coming straight towards him or her. If it is if it is less than, if it is 1.01 times V upper, what would happen?
So it will swing after the ball releases from the
Almost after,
bowler's hand.
immediately, yes, immediately after it comes out of the hand. So the batsman will have more time to change his or her stance if required, because she can see the ball moving in a specific direction almost immediately afterwards. So the reaction time would be more. But if it is around midway, if it starts to move in a specific direction, what a perfect leg swing should do, then there is almost no chance to change your foot and back position to meet such an incoming or outgoing ball. So is it clear to all of you? I thought that this would be a very interesting problem to end our discussion on boundary layers, many facets of which I did not touch upon, but these are the basic fundamental things that one should know as a part of the transport phenomena course. So if any other question that you may have? Okay, so in that case, I will close this class now. We'll have a test on Wednesday, and I will upload this immediately after this class. And the syllabus for this would be Navier-Stokes equation as well as the boundary layers. And from the class after that, I will start with heat transfer, mass transfer, and subsequently, finally, with the analogy between the three processes. So if there are no questions, then I'll stop the class here. Thank you once again.
Thank you, sir.